Yeah, so just let me introduce myself. I'm Manuel Aravena. I'm a professor at the Universidad Diego Portales in Santiago, Chile. And I'll be talking today about something, well, given the main overall topic of this conference, I thought it would be good to just introduce a little bit some kind of recent science or novel approach doing ALMA surveys of cosmological deep fields. So I'll be talking very little about or reviewing some of these efforts done to do this, and also at the end I will focus on one particular one, which is called the ALMA spectroscopic survey of in the Hubble Ultra Deep Field, which is from which I'm part of. Um, one of the main important questions in galaxy evolution and formation is to understand how the galaxies evolve through cosmic time, not only from a observational perspective, but also through a theoretical perspective. Um, in this simulation, you can see that galaxies grow through accreting gas from flows or inflows of gas from the intergalactic medium. And this situation has been constrained very tightly and very nicely from simulations. And this is what also Guillermo showed in his talk at the beginning of his talk a few minutes ago. However, from a very zoom out perspective, uh, we also have some constraints on this from a observational perspective. Um, oh, what happened? Okay. So here I'm showing the cosmic evolution of star formation rate density of the universe, the famous Lilly-Maddow plot. And starting at high redshift, this star formation rate density increases, peaks at around redshift of 1.5 to 3, which it's a cosmic age of about 5 gigayears, and then drops by an order of magnitude to the local universe. So this has been very fundamental in our understanding of how galaxies evolve with cosmic time. And then if we want to integrate the star formation rate density, one can calculate the stellar mass that is being formed. And this is shown as the dashed orange line in the top right panel. But actually, if you compare that to simulations here, the actual stellar mass that is being observed in the near infrared imaging is here shown as a red line, and it is lower by about a factor of 50%. This is because stars lose mass during the star formation process, and essentially through stellar winds and supernova explosions. And not all the stellar mass form will stay in stars. Therefore, now let's turn now to the gas phase, and let's first look at the evolution of the atomic hydrogen. The compilation shown here combines H1 emission data in the local universe and H1 absorption data at high redshifts. And for about a decade now, there is the consensus that that change in H1 density is very modest. So it stays relatively constant through cosmic time, with about a decline of only a factor of 2 from the high redshift to present day. So the missing piece of the puzzle in this evolution of the molecular gas density, sorry, the missing piece of the puzzle is the evolution of the molecular gas density, the actual gas out of which stars form. And this is a key measurement that has just recently been constrained. I have indicated here some previous constraints from the IRAM Plateau de Beer data efforts, which gave some of the first constraints. However, they have very large error bars. So this observation, though, laid the foundation from some ALMA programs and trying to constrain this parameter. So since we're talking now about molecular gas in galaxies, I just wanted to remind everybody which part of the electromagnetic spectrum we're talking about. So here I'm showing the spectral energy distribution of M82 that can be separated into the various physical processes that give rise to the final observed spectrum. So as you can see here, shown in gray, which is the total intensity, This shows the continuum, but also you can see a bunch of emission lines. And in particular, you can see the H alpha, the pHs, the O1, C plus, and CO carbon monoxide molecule. These lines, particularly in the sub-millimeter regime, are key to actually constrain the cold ISM. And because most of these emission lines, the dust and features are actually good tracers of the ISM and molecular gas content and star formation activity. So in particular, the CO lines, dust emission in the Rayleigh Jeans regime, but also some other lines like C1 and C2 are key for understanding and have been used so far. So this is actually of why many galaxy surveys of molecular gas and dust at high redshift have been performed over the last decade, leading to dozens of papers that we will not try to summarize here. But as I was mentioning, the most used tracers so far have been the dust continuum, the CO, C1, and C plus lines. And in particularly, the dust continuum has been extremely efficient at detecting the ISM from high redshift galaxies. Um, and you can see that there are thousands of galaxies having been observed with ALMA from redshifts 1 to 4. And in particular, another interesting line or observations that you can do is using the C plus line, which has been key to characterize galaxies at redshifts above 4. And that's because this line enters into the observable band from ground with ALMA and with other telescopes. So I'm showing actually two examples here. The first one corresponds to high resolution observations of a very massive star-forming galaxy at a redshift of about 1 from the fifth survey. And the fifth survey has been key to actually lay a foundation of how galaxies are evolving. But I also show a recent C plus detection from a rotating disk galaxy at redshift 6.8. The interesting thing is that we can not only use these lines to actually measure the ISM content, but also to measure the dynamics and their overall properties, particularly at high redshift, where it's really hard to interpret and to lead to these sensitivities and features. So one problem here has been that most of these surveys done at high redshift have been targeted observations of pre-selected galaxies, which have been pre-selected using their UV and far infrared properties. So despite the super success of all these surveys that are listed here, the main limitation has been their pre-selection. So one of the complementary approaches is to observe a cosmological deep fields where we have a wealth of ancillary data, including redshifts, and look for dust and molecular gas emission directly. So this approach is not new, as many cosmological deep fields have been observed in the past at the sub-millimeter using bolometer cameras. However, the new thing and the leap here is to use ALMA to observe some of these fields. And the idea being that ALMA has 10 to hundreds times more sensitivity. Therefore, you can not only grasp the very brightest sub-millimeter galaxies or bright starbursts, but also go into the more normal population of galaxies and see how they are evolving as a function of cosmic time, stellar mass, etc. So here I showed some examples of these deep fields done in the last 5 years, I would say, not 10 years, but only 5 years, where various regions of the sky have been mapped covering different areas and depths, and mostly following a wedding cake strategy. So the smaller surveys are going deeper and the wider surveys are just going wider. And in some cases, like the Hubble frontier fields or the ALCS survey, the ALMA cluster lensing survey, the idea has been to use the help of gravitational lensing to enable the detection of very faint galaxies or very high redshift galaxies, while in other cases have focused in key regions of the sky, like the candles, the good south, the cosmos field, and the Hubble ultra deep field. So all of the surveys to date, however, with the exception of the ALKS survey, have focused on the detection of dust continuum emission only. So essentially using a single setup with ALMA, observing and collapsing this single setup and obtaining a deep continuum image of 1 millimeter or 870 microns. Um, and most of them have been done down to shallower depths, not really going very deep, trying to grasp the faintest objects. Um, we have recently finished the ASPECT survey. ASPECT stands for ALMA Spectroscopic Survey of the in the Hubble Ultra Deep Field. And here we targeted the deepest region, the extremely deep field, through mosaics in ALMA band 3 and band 6. We then scanned these bands in frequency, as is indicated to the left-hand side here. Our plotted are the redshifted frequencies of CO lines that we use to measure molecular gas content in galaxies. And as you can see, these lines pass through ALMA bands 3 and 6 as a function of redshift. So by using these two bands, you can actually obtain a lot of information of different lines through different redshifts. And also you can target C plus line at redshifts between 6 and 8. So one important thing about covering the Hubble Ultra Deep Field, or the XDF, is obvious here in this image. It has the deepest observations ever obtained with the HST and with MUSE through their GTO programs, and will soon be targeted by JWST, not only in GTO programs, but also in open time programs. And this gives a unique complementary data set in order to understand the multiple components of the galaxies in study. One interesting thing also is that, as you probably know, in the MUSE image, you actually get one spectrum at every pixel. So this is exactly or very similar to what we're doing with ALMA, since we are also obtaining a spectrum at every position in this region of the sky. So here I'm showing the ALMA mosaic pointings in bands 3 and 6 in green and yellow respectively, so you can actually see how this was performed. There were around 17 pointings in band 3 and 85 pointings in band 6. And again, scanning the full ALMA band 3 and band 6. So before going further, I would like to say that this project was made possible by a wide and large team of experts of different areas. So if you want to learn more about aspects, please visit our website. You will find lots of informations, visuals, videos, and images that you can also use in your talks or in your work. And the actual data is also available there. And in the following, I will just concentrate in just a few results of the aspect survey. However, given the richness of the data sets and the complementarity with HST and so on, aspects has been capable of informing a wide range of science topics. So I would recommend you to check our publications to learn more about other key results from aspects. Well, here are some of the additional publications which I'm not going to be talking about. So here you can see the actual ALMA band 3 and 6 data cubes in the UDF. Given the number of independent beams and frequency elements, or whatever you call them, spaxels, it is hard to see the individual detections. So I have to point them out a little bit here. So it's easier with a little help. And these are definitely not all the detections that we have obtained, but just the most visible in this data cube. However, the point to make here is that we're blindly detecting or obtaining constraints on CO line emission, C1 and C plus line, also dust continuum simultaneously in all the galaxies for the UDF. So with the aid of MUSE and HST images, we can perform guided searches and stacking analysis aside from individual detections. So indeed, when you collapse the 1 millimeter data cube after removing all the spectral lines, you can get a very sensitive continuum map of the UDF. So this is shown here at the left-hand side. This is the 1 millimeter map, and you see that we reach an RMS of 9.5 microjans in band 6. This is by far the most sensitive dust map ever obtained for a deep field with ALMA. And here we have detected 50 galaxies in continuum emission. So as you can see at the right-hand side, aspects among all these similar surveys is now reaching the deepest levels in this direction. So here we show which galaxies in the UDF are detected. So in here you see the blind 1 millimeter detections as blue, the faint 1 millimeter detections, which are actually based on priors. So you know that there is a galaxy there, and then you try to see whether there is a 3 to 4 sigma dust detection or continuum, or sorry, or CO detection and so on. And also the CO line detections in band 3 in magenta. So this is just to make you an idea of the kind of data that we are having. So one interesting result from the continuum map that you just saw is the flattening of the cumulative 1 millimeter number counts at very faint fluxes. So in other words, that means that we're finding much less faint sources than predicted based on earlier surveys and extrapolations to the faint end. So we now understand that this flattening is likely due to the stellar mass function in galaxies at redshifts between 1 and 3. So for more details on that, please go to Gergo Popping's paper 2019. So also this flattening means that by performing deeper observations, we will not really obtain many more detections of dust continuum, or that the rest of the galaxies in the UDF have very little dust or quite different dust properties, such as different dust temperatures or other different properties. So this is quite interesting. There is also the question whether this is only something about cosmic variance with the UDF alone, or this is happening broadly. So we will know more about that when there are some other surveys that are being performed, and when they publish the results, such as the ALX survey that I was mentioning before. So here you can see a showcase of all the CO, some of the brightest CO detections and dust emitting detection. And you can see that the galaxies that we're detecting span a very wide range of properties. Most of them have near infrared counterparts, and that's a very interesting thing, because there have been the claims that there are all these dark HST dark galaxies, but in this case we don't find any HST dark galaxy in the UDF. And we believe that one of the reasons might be that the UDF goes so deep in HST imaging that really you are detecting everything that you can. And the other surveys are not detecting this just because of lower sensitivity of the HST images. In the following, I will try to go quickly through the properties of detected galaxies, and I will try to summarize the main properties in just one slide. So first, it's the redshift distribution of the dust continuum detections. We detect galaxies up to redshifts of 4, actually. And compared to some millimeter galaxy surveys, the distribution peaked at lower redshifts, so at a redshift of around 1.7. As you can see here, the magenta here shows the SMGs, the submillimeter galaxies, and the solid black line shows the aspects redshift distribution. So definitely a lower median redshift than the SMGs. So next is putting the galaxies in the typical main sequence context, where galaxies are shown as points in the star formation rate stellar mass plane. And as you can see, we detect galaxies above, on, or below the main sequence, indicated as color lines for different redshifts. And this is entirely due to the observational approach. So particularly the fact that we have not preselected galaxies based on optical properties. And here the blue contours show the distribution of all galaxies in the HUDF. So in the third panel, we show the star formation rate of the aspects galaxies as a function of the molecular gas mass. So on average, we derive the gas depletion timescales of about 1 gig a year, similar to the FIPS survey. So in that sense, it's pretty consistent to what other surveys have been finding. And finally, the fraction of molecular gas mass to stellar mass as a function of redshift. So our galaxies approach gas to star or to stellar mass fractions of around unity at high redshifts, which is consistent with what other people was finding, even though our galaxies have a little lower gas fractions compared to other observations. And this should be compared to the value of zero point 0.1 in the local universe. So galaxies at high redshifts are much more molecular gas dominated than locally. And that was demonstrated earlier through targeted studies. One interesting thing here is that we're not selecting or pre-selecting galaxies in the MS in the top right-hand side plot or above the MS, so starburst galaxies. Here we are actually obtaining a bunch of galaxies below the MS as well. And that's one very interesting subject, which we can talk more about later if you like. But this is just by definition of the idea of this survey, just doing it blindly and not targeting galaxies. So I'm running out of time. So just let me go back to the data cubes, and we can use the aggregate CO emission in our cubes to derive the CO luminosity function in 4 redshift bins as shown here. And here I'm showing the resulting H2 mass functions in the top x-axis. The red shaded areas are our data. So we are covering the knee of the luminosity function. So overall, more than 50% of the emission for this at different redshifts. And by integrating the H2 mass functions in the respective redshift bins, we can obtain the evolution of the molecular gas density as a function of redshift. So the results are shown in this plot here, where we show the cosmic molecular gas density as a function of loopback time or redshift. And this figure summarizes one of the core results of the aspects program. We performed independent measurements of these based on dust emission and CO emission and finding some very similar results. So the interesting thing here is that the cosmic molecular gas density actually follows very tightly the star formation rate density. It shouldn't have necessarily been like that. It could have been different. So what this is telling us, we can add actually the missing piece of information in the slide I showed earlier about the molecular gas density of the universe. And it looks like this. Putting all of the current constraints together from aspects and from other surveys, you get a summary plot like the one shown here. So you have all the different components of the cosmic baryon cycle, but from an observational point of view, not as theoretical point of view as we had been looking in the past. So these are probably the first tight constraints on this. So we can now plot all of these different cosmic mass densities in the same plot. And here we show this, and also we overplot the cosmic baryon density and the dark matter density for reference. So you can see that at redshifts of about 1.5, the molecular gas density reaches that of H1. This here with the arrow, I'm showing there that redshift, but it stays below the H1 at all other redshifts. So here the molecular gas density is shown in purple, and the H1 is shown in green. And at the same redshift of 1.5, the stellar mass density shown in red here surpasses that of the total gas, which is H1 and H2. So here you have a very critical period of cosmic time where you can actually have things happening. So if you actually consider the cosmic mass gain or loss from galaxies, and particularly the stellar gain and the H2 loss and the H1 and gas loss in general, you will see that from redshifts 1.5 on, you have a significant stellar gain here, which is shown here in red, but then this is not compensated by the loss in H1 and in gas overall. So there is something from which stars are growing that is not necessarily coming from the content of galaxies themselves. So the thing that is needed here to explain the stellar mass growth is accretion. And this is probably one of the first constraints on this, based on observations alone, putting all the pieces together. So I have a few more slides, but I'm actually going to stop here.